All right, let's have a look at the first question here. We've got the square root of 64 plus the square root of 144. Well, if I think properly, the square root of 64 means I'm looking for a number multiplied by itself that gives me 64. And that number is 8. And the square root of 144 would be 12. So the final answer is 20. Moving on to the second one here. All right, I know that the value of each of these is 1. So I'm just going to add them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this side is 10. Because it's balanced, I know that this side is also 10. Well, within that 10, I can eliminate these two, which are each worth 1, which means that everything that's left has a value of 8. So the answer here is 2. Well, this question should look familiar. We looked at questions just like this yesterday. So I've got a function table. Couple ways I could do this. I could keep going all the way down until I get to 25, but I don't want to do that. Instead, I want to try and come up with a rule. Well, I could try adding 3. That doesn't work. Multiplying by 4. That doesn't work. Well, what if I multiply x by 3 and then I add 1? That's going to work every time. So if I take 25 times 3, that's 75. Add 1, 76. $16 is what percent of 50? Well, $16 over 50 is how much over 100? $32, so the answer is 32%. All right, moving on to the second page, we're starting off with dividing fractions, something we haven't done yet. But if we just think about what division means, if I take a question like this, all it's asking me is how many times does 2 go into 6? Well, I know that 2 goes into 6 3 times. If I'm looking at fractions, it's the same idea. How many times does 1 go into 2 3/4? Okay, how many times does 1/4 go into 2 3/4? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times. The answer is 11. Number 6. What is the area? Oops. Number 6. What is the area of an 8.5 by 11 rectangle? 8.5 by 11. This is mental math, which means we can't use a calculator, and we really don't want to have to calculate things. So I'm going to take 8 times 11, which is 88. 1/2 times 11, well, that just means what's half of 11? That is 5.5. So if I add 88 and 5.5, I get 93 5/10. centimeters squared. All right. Last question. The square root of 70 is at which of the following points on the number line? All right. Well, if I think about the square root of 70, I'm going to think about the square root of 70 is at which point on the number line? Well, if I look here, I know that 8 squared, I'm looking at 64. 9 here would be 81. So if I look, 70 is much closer to 64 than it is to 81. This is the midpoint, so I must be looking at A. So right now you want to be looking at page 478 in your homework book, and you also want to have your journal open to page 10. So we're going to take a look at the idea of linear relations, the title of this unit. What is a linear relation? Well, it's a pattern made by a set of points that lie in a straight line. So you're going to hear this over and over again, linear relation, straight line. Anytime we don't have a straight line in our graph, we do not have a linear relation, which simply means that there is no actual pattern. So we're going to take a look today at how we can take the information found in a table of values or found in a pattern and turn it into a graph. So what we've got here is our first example where we have x and y. And when you look at this, you have no idea what x and y represent, which is why we want to try whenever we can to come up with variables, which are letters, that make sense. We're also going to take a look at what we call a table of values. Yesterday I referred to this as a function table. We need to recognize that function table of values, the same thing. So I'm going to have you start off by copying some information onto page 10 in your journal. I'll give you a little bit of time to do that. So obviously you guys have noticed by now that all of the words are all over my face, but there's nothing I can do about that. So we're going to take a look now at how to make a table of values from a graph. So this graph here shows the total cost, depends on the number of baseballs you buy. So happy to see a question about baseball. It makes me think of being outdoors, and to be honest with you, the only thing my kids have been able to play in the basement is baseball. So the total cost and the number of baseballs are related to each other. So if we look at our graph, it says here that variable b, which is on the x-axis, shows the number of baseballs. So I could buy 1, 2, 3, 4, any number of baseballs. And the y-axis is C representing the cost of baseball in dollars. Very important that we think back to what we learned in Unit 1 about making sure that we label the intervals properly, and we also label what it is that we're actually talking about. So what we're going to do here is try and describe some patterns that we see on this graph. We'll just scroll up a little bit so we can see everything. All right, so the graph shows data on the cost of baseballs. 1 ball costs $3. 2 balls cost $6. 3 balls cost $9. Are we starting to see a pattern? So the total cost increases by $3 each time you buy a baseball. Another thing that we have to learn to do is talk about how to move from one point to the next point. So if I want to move from one point to the next, I'm going to go 1 unit horizontally. So I go 1 unit horizontally. And how many units do I go vertically? Well, I go from 3 to 6, so I'm actually going 3 units vertically. The other piece is, if you remember, I said at the very beginning, what is a linear relation? Well, it showed points that lie in a straight line. And if we look at this graph here, we see that our points are all in a straight line, so we have a linear relation. Let's keep going. All right. So I've just copied this graph again so I can see it here while we're talking. So what we're going to do now is take this graph and we're going to turn it into a table of values. So what we need to do is read each point as an ordered pair to make a table of values and complete the table. So we may choose to do it horizontally like this, or we may choose to do it vertically. It does not matter. What you want to keep in mind is space on the page and what's going to look better, what you're more comfortable with. So we'll fill out the horizontal one first. In the horizontal table of values, the top row shows the x-coordinate, which is B, and total cost. You have to make sure not to mix those up. The first one has to be X, second one has to be Y, just like X comes before Y in the alphabet. Number of baseballs, $3. For 1 ball, $3. 2 balls, $6. 3 balls, $9. 4 balls, $12. Now I don't need to put in a dollar sign each time because it's already here on my graph. Exactly the same thing in the vertical table of values, only now we've got baseballs, cost. 1 ball, $3. 2 balls, $6. 3 balls, $9. 4 balls, $12. Easy enough to put things in a table of values. Oh, now things may get a little bit more tricky because we're going to take that table of values and we're going to make an expression out of it. Just remember that when we're making an expression, we have to look how to get from X to Y. Don't get caught looking from how to go from one to the next. We're always looking X to Y. And we're going to be thinking about our basic operations: add, subtract, multiply, divide. It's either going to be one of those or it's going to be a combination. So let B describe the number of baseballs. The expression 3B describes the cost of buying baseballs. So we have 3B, which means 3 times B. We do not ever want to write 3 times B because when we're looking at algebra, what does this mean? Well, it means X, and if we use it as a way of multiplication, things become confusing. So if we want to do 3 times B, 3B. 1 times 3 is 3. 2 times 3 is 6. 3 times 3 is 9. It will go on forever like that. If the relationship on the graph continues, how much will it cost for 14 baseballs? We're going to use that expression 3B to help us out here. So the cost of baseballs is simply going to be 3 times 14. What is 3 times 14? 42. The cost of 14 baseballs is $42. Don't forget your units. Next example, we're going to look at 2 patterns that we see on this graph. The points appear in a straight line. In a straight line. And to move from one point to the next, I'm going to start here and I move 1 horizontal, 1 unit horizontal, horizontal, And how many units do I move vertical? From 5 to 10 is 5. 5 units vertical. Great. The graph shows the number of squares, figure number of squares in relation to the figure number. These figures match the graph. Draw figure 4. All right. I see it goes from 5 to 10 to 15. So I'm just going to do this. All right, I've added one extra row here, so I have 20. Figure number 1, 2, 3, 4. 1, 2, 3, 4. Number of squares, there were 5, 10, 15, and 20. Is this a linear relation? Well, of course it is. The points are in a straight line, and we already mentioned that up there earlier. Let F describe the figure number. Circle the expression that describes the number of squares in any figure. Is it 5F or is it 5 plus F? Well, remember that if I'm looking for the expression, I'm trying to figure out how to get from X to Y. So it certainly can't be 5 plus F, because 5 plus 5 would be 6, or sorry, 1 plus 5 would be 6, and that's no good, so it looks like it is 5F. If the pattern continues, how many squares will there be in figure 8? Well, I've got my expression, 5F. I'm going to do some substitution. In figure number 8, we would have 40 squares. 40 squares, there's our final answer. Let's take a look at another example. This one's a little bit different. Nicole has a part-time job. The graph shows her pay related to the number of hours that she works. Describe the patterns you see on the graph. Well, the graph shows data on the pay Nicole receives for each hour of work. The pay for 1 hour is $10. The pay for 2 hours is $20. The pay for 3 hours is $30. My goodness, look at that. We see a pattern. The points lie in a straight line. So the graph is a linear relation. To move from one point to the next, move 1 unit horizontally and 10 units vertically each time. Put it into a table of values. 1 hour, $10. 2 hours, 20, 3 hours, $30. How much does Nicole make per hour? Well, we look at the table of values. In 1 hour of work, Nicole makes $10. For each hour she works, Nicole makes $10 more, so she makes $10 per hour. Now here's a really interesting question. Is it possible to have points between the points shown on the graph? Well, can I have a point right there? Take a second to think about that. Well, is it possible that Nicole could work part of an hour? Absolutely. So yes, we can have points between the ones shown on the graph. Yes, she can work part of an hour. Well, how much would she make if she worked for 2.5 hours then? Well, we know that our expression is $10p, okay, $10 per hour worked. So we could take 10 times 2.5. What is 10 times 2.5? That would be $25. So if she worked for 2.5 hours, she would make $25. You want to pause the video right now so that you can copy down the last piece that's going to go in your journal today, where it simply says that sometimes there can be points between the points on a graph. For this example, you've got the cost of banana chips at Bulk Barn, and they've got a whole bunch of different quantities here and cost. At Bulk Barn, you could buy however much you want, so you could buy 150 grams of Bulk Barn of banana chips there. Just remember, you can't always get points between the ones on a graph. You can't go to McDonald's and ask them for half a cheeseburger. They won't give you one. So as I said, pause the video, copy your notes. Last example that we're going to look at today, Chad is buying notebooks at Bob's Bargain Store. The graph shows the cost of notebooks. So we're going to describe two patterns that we see on the graph. Are the points in a straight line? They sure are. Points are in a straight line. And I move one horizontal for every 2 units vertical. 2 vertical. So if we look to complete our table of values now, we have the number of notebooks, 1, 2, 3, 4, and the cost. So we have $2, $4, $6, and $8. Use the table to find the cost of one notebook. Well, the cost of one notebook would be $2. Write an expression to show how much N notebooks cost. So remember, when we're looking for an expression, we're figuring out how we're getting from X to Y. Well, if I look each time, I am just simply multiplying by 2. So my expression is 2N. 2 multiplied by the number of notebooks. How much would it cost to buy 52 notebooks? Well, that would be very difficult if I just kept extending this until I got to 52. So instead, I'm going to use my expression, 2N. Substitute, 52. Solve, 104. Sentence, it would cost $104 to buy 52 notebooks. Is it possible to have points between the ones on the graph? Could I put a point right here? The answer is no, because you are not going to find a store that you can go to where they're going to sell you half a notebook. So we've got to pay attention to that.